We were doing time dependent scattering last time और नाउ आज हम बात करेंगे एसिम्प्टोटिक कंडीशन की। एसिम्प्टोटिक कंडीशन से मुराद ये है कि एट टाइम t is equals to minus infinity and at time t tends to plus infinity, the actual orbit which is at time t is equals to 0, that is the time at which the interaction is taking place. That is the actual orbit would tends to the orbit which is known as the asymptotic orbit, that is the orbit at t is equals to minus infinity, which is a free particle. Yeah. So what is the asymptotic condition? It says that the actual orbit u of t is the unitary operator evolving the state function psi. So the actual orbit would be u of t at acting on psi, uh, would tends to an asymptotic orbit at t is equals to minus infinity, and similarly this actual orbit u of t tends to an asymptotic orbit at t is equals to plus infinity. So at t is equals to minus infinity, the free orbit is denoted by psi in, and whereas the at t is equals to plus infinity, the orbit is denoted by psi out. So what we need to do, we need to establish that every vector in the Hilbert space, every vector in the Hilbert space, that is in fact psi, all the psi in and all the psi out, whatever the labeling condition you are adopting. So all the vectors in the Hilbert space denoted by or labeled by psi in or psi out does represent the asymptote of some actual orbit. Asymptote of some actual orbit का मतलब है that is the free orbits. Yeah, that is for every vector psi in or every vector psi out in the Hilbert space, there is a solution of this actual orbit u of t of psi of the Schrödinger equation that is asymptotic to the free orbit, which is basically denoted by u naught of t psi in. And similarly, this applies for the psi out as well. So we start with the asymptotic condition. So what we need to do first of all is to establish the idea that every vector in the Hilbert space that corresponds to the asymptote of some actual orbit. This is basically some sort of a mapping between, and that is what we actually need to do. That is आगे चल के हम मोलर ऑपरेटर डिफाइन करेंगे. And this what we are trying to do is to map the vectors in the Hilbert space to the space of scattering, space of states of scattering, and vice versa. That is, every vector in the space of states of scattering can be mapped onto the Hilbert space. So this is what we are basically considering. So what we need to establish first. So need to establish that every vector in Hilbert space may be labeled by psi in or psi out. Yeah, does represent some sort of some does represent the asymptote of some actual orbit, of some actual orbit. क्या मतलब है इसका? i.e. for every vector psi in or similarly for psi out in H, that is in the Hilbert space, there is a solution uh, u of t of psi of Schrödinger equation that is asymptotic to, that is asymptotic to some free orbit, to free orbit, which is basically written as u naught of t. Rather than u of t, we write it as u naught of t acting on psi in at or as in fact t tends to minus infinity. And similarly, this is also true for similarly is true for t tending towards plus infinity. That is what we can say, that for every vector psi out in the Hilbert space, there is a solution u of t of psi of Schrodinger equation that would be, that is asymptote to free orbit u naught of t, but acting on psi out as t tends to प्लस इन्फिनिटी. तो ये पूरी जो आपके पास यहाँ से यहाँ तक स्टेटमेंट है, that can also be written for the psi out as well. Yeah. तो हमें सबसे पहले ये कंडीशन जनरेट करनी है, यानी ये स्टेब्लिश करना है कि एवरी वेक्टर इन साई इन every vector in Hilbert space, but whether that is psi in or psi out, that would correspond to the asymptote of the actual orbit. Yeah, actual orbit is ut of psi. और इसको हम we are basically thinking about a potential which satisfies the condition जो हमने इससे पहले लास्ट लेक्चर में डिस्कस की थी, that the potential is spherically symmetric, and then हमने वो तीन conditions इस्तेमाल की थी, and based on those three conditions we will prove this. So if so mathematically इसी चीज को जो हमने अभी लिखा है, हम कहेंगे if V satisfies का मतलब we are talking about a spherically symmetric potential. If V satisfies the conditions जो हमने 0 to 3 पहले बात कर चुके हैं, then for every psi which belongs to the Hilbert space, there is a psi such that u of t, which is acting on psi. So this is the actual orbit minus u naught of t acting on psi in tends to 0, when जब t is tending towards माइनस इन्फिनिटी. सो दिस इज द डिफरेंस. सो वो चीज़ जो हमने ऊपर लिखी है उसको मैथमेटिकली हम इस तरह से लिख सकते हैं. एंड सिमिलरली वी कैन राइट इट फॉर द आउट एज वेल, दैट इज एट टी टेंस टू as t tends to plus infinity. So this condition says that for all the orbits, for every orbit in the Hilbert space, or for every vector in the Hilbert space, psi in or psi out, there is a corresponding vector psi such that this corresponding vector psi obey this condition. That is this, in fact, condition which says that the actual orbit psi minus the free orbit psi in tends to 0 as t tends to minus infinity. And this is true for all orbit. That is, we would say that is for all possible asymptotic free trajectories. Three trajectories, i.e., psi in where there are corresponding interacting trajectories psi. Yeah. So you can see we are basically relating psi in with psi, and that is it tends to a free trajectory. दूसरे लफ्जों में we are saying that this interacting trajectory psi, it is tending towards a free trajectory psi in. Psi in का मतलब है that is the vector at t is equals to minus infinity. Psi out का मतलब है कि that is a vector at t is equals to plus infinity. So we are saying that there is a correspondence between interacting trajectories. Or what are interacting trajectories? Those trajectories at the time t is equals to 0, that is at the time of interaction of a particle with the target. That is basically the interacting trajectory, जिसको हमने psi से जाहिर किया यहाँ पर. That is, इसका मकसद क्या हो गया? i.e. it tends to, that is this trajectory, that is this psi tends to uh, free trajectories. Yeah. And similarly, this goes for all the outs. Similarly, we could also, to complete the discussion, similarly for all possible asymptotic asymptotic out trajectories, they correspond interacting trajectories. Right. Yeah. That is, it tends to free trajectories or trajectories rather. कैसे? U of t psi minus u naught of t psi out tending towards 0 as t tends to plus infinity. So this is in fact the condition. अब हम इसका proof करेंगे. That is uh, whatever we have said here, that is the interacting trajectory t psi is tending towards free trajectory at t is equals to minus infinity and t is equals to plus infinity. So we need to prove this. That is, ये जो दो statements हमें नजर आ रही हैं, this statement, इसको हम let's say अगर मैं इसको वन कह दूं, सो दिस इज वन. और जो दूसरी स्टेटमेंट है, दिस इज इन फैक्ट टू. इन दो स्टेटमेंट्स को हमें साबित करना है. सो लेट्स टॉक अबाउट अ प्रूफ. Yeah. So let's say we assume some unitary operator u of t. Um, that is, unitary का मतलब है it is invariant and under transformation. So let us assume unit u of t as some unitary operator. That is, we assume that u of t exists as a mathematical object. And so if u of t exists as a mathematical object, then u dagger of t, that is its complex conjugate, would also exist. And then we multiply these two equations, equation 1 or equation number 2, with this complex conjugate. So assuming u of t is unitary, i.e. uh, we assume that u of t exists as a mathematical object. Therefore, now let's say we multiply, now multiplying 1 by u dagger of t. uh, so क्या हो जाएगा, so we would have u dagger of t into u of t psi minus u dagger of t into u naught of t psi m. Yeah, and this is this tending towards 0 at t tends to minus infinity. This is the condition. So uh, this would imply that this is equals to 1. This is equals to 1. Yeah, so we would have psi minus u dagger of t, u naught of t psi n tends to 0 as t tends to minus infinity. Yeah. That is, हमें क्या करना है, we need to show that this u dagger, that is जो second term है left side पर, that is u dagger of t, u naught of t psi n has some limit. Yeah, and अगर it means when it has some limit, then the difference of these two would be equals to 0 at t is equals to minus infinity. So what we need to show, we say we need to show that u dagger of t, u naught of t has a limit. A limit as t tends to minus infinity. This is the limit we need to find out here. And इस limit को निकालने के लिए what we need to do, we need to talk about, the first step would be to prove that there is this limit to the second term, that is the term, इस equation को अगर मैं equation number 3 कह दूं, so in this third equation the second term has a limit, and maybe there is a case where the limit where the limit is in the form of oscillation, that is it oscillate, and if it oscillate, then it would not have a limit, that is some sort of a bound state. So but we are talking about a limit where it does have a limit, so it would not be an oscillating state, it would not be some bound state. So we could think about, जैसे हमने पहले बात की थी कि a particle comes in towards the target and there is no out state, and that is only happens when the target captures the incoming particle, and then that incoming particle becomes the bound state of the target. So uh, what we need to do is to, the first step would be uh, so the first step is to prove is to prove that there is a limit. There is a limit to this second term. Yeah. Okay. Maybe there is a case where you could think about that there is no limit. Yeah, does not have a limit. Uh, Maybe there is a case where there is where there is no limit, that would correspond to some oscillating state, i.e., bound state. So this could be thought of. So particle comes in. What do you mean by bound state? But that is particle comes in, and this particle then oscillates back and forth and never settles down as an asymptote. And so this would correspond there to something which is an oscillating state or a bound state. So this implies that a particle comes in and oscillates as a bound state and never settles down, never settles down to some limit, some limiting state. Yeah. So what we need to do, हम ये नहीं करना चाहते, ये तो मैंने जस्ट एक असाइड इफेक्ट हमने बात की. So we are not talking about this. So maybe there is this bound state, but what we are considering it not the bound state where the particle comes in and scatters in the out state. So what is basically we are interested in? We are interested in that ut of u dagger of t times u naught of t uh, psi n has a limit. As a limit. This is what we are interested in. And so to prove this, यानी दूसरे लफ्जों में has a limit. When it has a limit at t is equals to minus infinity, then equation 1 is correct or equation 2 is correct for the outstate. So to prove that this something का मतलब this particle has a limit and has a limit at infinitely far past or infinitely far in far future, the fundamental theorem of calculus can be used. And what is that fundamental theorem of calculus? It says that the derivative of a derivative of some integral is basically equals to sorry, derivative is equals to its integral. Yeah, derivative is equals to its integral का मतलब ये कि we take the integral of a derivative, then that corresponds to some in fact some function which is basically equal. So we differentiate, and so this is a two-way process, the reciprocal process. So derivative is the reciprocal of integral, and the integral is a reciprocal of a derivative. So we can integrate a differential equation to get a function, or likewise in the opposite direction. So this is basically some you can think about as a theorem, but this is something which we have learned from lower classes as well. That is the integral is the derivative of a function. Yeah. So so to uh, that prove that something something means some particle has a limit, has a limit. In our case, this would be particle. In general, that something is whatever some mathematical representation has a limit in infinitely uh, far past or infinitely far future can be proved using the fundamental mental theorem of calculus, i.e., the derivative, the integral, rather, integral of a derivative of a function is a function. Yeah, i.e. कैसे करेंगे? So one differentiate, basically one differentiate and integrate बस दूसरे लफ्ज़ों में. So one differentiate and integrate. Yeah. And so this would imply u dagger of t, u naught of t. अभी हम इसकी बात कर लेते हैं. Is would be equals to some integral 0 to t ds u dagger of s सम फंक्शन. ये कहाँ से आए, दिस अभी हम कैलकुलेट कर लेते हैं. u नॉट ऑफ टी डी एस प्लस सम फंक्शन, या प्लस सम अदर फंक्शन, ये बात हो जाएगी. सो इधर से ये बात अभी हम जनरल कर रहे हैं, अभी हम अपने केस पर आ जाएंगे. सो इफ समथिंग हैज अ लिमिट, देन इसका मतलब क्या है, इट इज द इंटीग्रल ऑफ अ डेरिवेटिव. And if something has no limit, does not have a limit, then it is not an integral of a derivative. So then you can prove that it has. So in order to prove, or to prove that it has a limit, then you take the derivative of that function. So if something, some representation, some mathematical representation of some physical phenomena. So if something has a limit, then that something, it's the integral of a derivative. Then you can you can what you can prove that it has a limit. You can prove that that it has a limit by showing that it's showing that its derivative is small, so that when you add something, when integral is basically adding, so you when you add it all up, it does not diverges. It not does not add up to too much. Add up to too much. What does this mean? Add up to too much. That is, it does not diverges. Yeah. So whenever you take the integral of a derivative, then basically what you are doing, you are basically adding those small pieces. Yeah, because derivative is dividing the whole into small pieces. Yeah. So whenever you take a derivative of sorry, integral of a derivative, so what you are doing, you are basically adding up small pieces. So when you add all those small pieces, and you come up to a value which is not too much, then that is in fact a limiting value. But if you add up to a value which is too much, then it implies that it diverges. So it does not have a singular solution. Yeah. So that is basically something about singularity. So in fact, it does not have a limit, implies that when you add those derivative, you add it to a too much value, to a very large value, which is same as in fact diverges. It does not converge. Yeah. So what you have a trick here. And what is that trick? You write u dagger into u naught, that is the product of u dagger and u naught, as the integral of its derivative. So the trick is to write u dagger u naught as the integral of its derivative. That is, you differentiate u dagger of u naught, and then this is equated to integral of this quantity. So this is something which is very simple, and it is in fact the fundamental postulate or fundamental theorem of calculus, because you say that integration and differentiation are reciprocal to each other, and so when you integrate the derivative of something, you are basically adding those small pieces of that something to a value which you are basically hoping to come to a limiting value. Yeah. But if that value comes out to be non-limiting value, then it means that is it is diverging. So इसी चीज को हम mathematically कैसे लिख लेते हैं जो हमने बात की. The trick is to write this u dagger of u naught as the integral of its derivative. So in derivative किसका हो जाएगा? d by dt u of t dagger, कहीं भी dagger यहाँ लगा लें, यहाँ लगा लें, u naught of t is equals to किसके बराबर? this the integral of this quantity, and the integral of this quantity would be iota e to the power iota ht. Then we have h minus h naught. सो दोनों से आपके पास एक से h निकलेगा. सो एक दफ़ा आप इसको डिफरेंशिएट करेंगे, इसको एज इट इज़ रखेंगे, यानी एक दफ़ा इसको डिफरेंशिएट करेंगे, इसको एज इट इज़ रखेंगे, और एक दफ़ा इसको डिफरेंशिएट करेंगे, इसको एज इट इज़ रखेंगे. एंड ईच टाइम, और ये क्योंकि यू डैगर कॉम्प्लेक्स कॉन्जुगेट है, सो इफ ई टू द पावर आयोटा एच टी यू डैगर ऑफ टी को रिप्रेजेंट कर रहे हैं, देन यू नॉट ऑफ टी जो है वो ई टू द पावर माइनस आयोटा एच नॉट टी के बराबर होगा. सो देन वी हैव ऑन द अदर साइड वी वुड हैव ई टू द पावर माइनस आयोटा एच नॉट टी के बराबर. या एंड दिस क्वांटिटी, जैसे मैंने आपसे पहले कहा था, ये किसके बराबर है? दिस इज सम ऑपरेटर वी ऑपरेटर. सो दिस थिंग would then become, that is the derivative of u dagger of t u naught of t complex conjugate would be equals to किसके बराबर? iota u of t dagger और v operator some operator h minus h naught u naught of t. और remember h naught क्या है? The free Hamiltonian. H क्या चीज है? The interacting Hamiltonian. So the difference of free Hamiltonian minus the interacting Hamiltonian would be some operator or some potential V. So this would give you क्या चीज? This gives जो हमारी इक्वेशन नंबर जो हम इनफैक्ट साबित करना चाहते हैं. So this gives u of t dagger u naught of t acting on psi in with b equals to किसके बराबर? psi in plus some value which is iota integral 0 to t ds u dagger of s. V is the operator, u naught of s times ds, or then we have psi in. Yeah, and this to at converge as t tends to minus infinity. So this is basically what we are looking for. That is, it converges at t as t tends to infinity. So this is basically known as the sufficient condition. That that is, this is true. That is, the norm of the vector in the second term goes to 0. This is only true when the norm of the vector. So this is in fact the sufficient condition. I is true then the norm of the vector in the second term जो ऊपर हमने लिखी है, that is the integral वाली term, second term goes to zero, and that is what we intend to prove. Okay. So that is what we intend to prove. So this is the sufficient conditions here. So let's talk about this sufficient condition. So what is the sufficient condition? Sufficient condition is integral integral minus infinity to 0. That is t is equals to minus infinity to 0. That is we are integrating all the way from minus infinity to 0 ds द नॉर्म हमने एक बात किया कि जो सेकंड टर्म है वो सिफर हो जाए सेकंड टर्म का क्या चीज द नॉर्म ऑफ द वेक्टर नॉर्म ऑफ द वेक्टर से किसी नॉर्म ऑफ द वेक्टर का मतलब है इनफैक्ट नॉर्म रिप्रेजेंट्स हाउ मच यू स्केल अ वेक्टर हाउ मच यू स्ट्रेच और हाउ मच यू मैग्निफाई अ वेक्टर और sort of demagniFy a vector, yeah, that is use how much you scale a vector, that is in fact your norm. So norm of a unitary operator is always V1 because it is invariant under transformation. So you say U dagger of S V